Wheatstone bridge. And again, the Wheatstone bridge is essentially it's a way of improving measurements. So it's a measurement instrument, and it's based on differential measurement, which means comparing from one to another in order to solve. And so, like I said in the previous little intro slide, it only works because of the balance condition IA equals 0. And IA, if you look over on the picture on the right, is the current flowing through that ammeter. So it needs to be able to say 0 amps of current or 0 milliamps of current going through the ammeter means the system on the left and the right hand side is balanced. And so this system is a way of determining an unknown resistor. And in this picture, it's called Rx. And then the known resistor that changes is R3, which is like a potentiometer. And that is a resistor that we can plug in and out. And if the resistance and the system is balanced and there's no current going through the ammeter, that means at point V1 and V2, there is no potential change. Because remember, you need to have a difference in voltage to be able to have current flowing. If there's no, excuse me, there's no difference in voltage there, no current is flowing between those 2 points. And that means all the current is flowing from the top of the circuit down to the bottom of the circuit the whole way through each of those resistors, except the ammeter, because that would be 0. And if we set the V1 equals V2 and we plug in the numbers for the resistances, V equals IR, how we normally do it, and then we simplify it, we're going to get out, when it's a balance condition, Rx equals the resistance of R2 over R1 times R3. And this is the way we're going to be able to solve what the Rx is at any given time. This is kind of a neat and handy circuit. We're going to talk about some of the sensors that you can use for this and some of the applications. It's a really good standalone circuit, actually, to be able to determine unknown resistances. And so if we go back through, we know that a lot of sensors are based on resistance. That's how we've designed the sensors, or just think of like a temperature sensor that we previously talked about. Temperature sensor can have 2 different methods. One, that when the temperature increases, the resistance decreases, or 2, when the temperature increases, the resistance increases. There's both types. And so usually the ones that we'll use in class and whatnot are as the temperature increases, the resistance decreases. But we'll look a little bit more at both types going on. I'm pretty sure I have those already for lab. So with that being said, this equation down below will allow you to determine what that resistance is. And if you know that resistance, there's usually a chart that maps it to temperature. And so that'll give you a very accurate temperature reading. So to ask again then, what are the downsides of the Wheatstone bridge? Well, downside 1 of the Wheatstone bridge is it's very dependent on knowing the resistances of R1, R2, R3, and being able to have those tightly controlled. So a lot of the resistors that you can buy for most electronics are plus or minus 20%, plus or minus 10%. And remember, we talked about that by looking at the bands on the resistors and the color coding. So if we have resistors that are 20%, this isn't going to be super, super accurate. But if you buy higher tolerance to resistors that are plus or minus 1%, plus or minus 0.5%, you can start to get some really, really accurate answers here for determining what Rx is. And so again, the determination and the resolution that you're going to get is based on the quality of the parts that you're going to use as well. So that's another thing to keep in consideration, because that's one of the downsides of using a Wheatstone bridge. You have to have very accurate resistors. And 2, another thing is, since this is an analog-based circuit right now, you need to have that ammeter in there and have it be read in order to solve what Rx is. And so there is not really for this circuit, it's not going to spit out a digital reading. It's going to be, you have to kind of balance it to get that ammeter set to 0, and that's going to give you your resistance of Rx. So there's a couple different smaller downsides, but in general, this is a really useful circuit to have anytime you're trying to do measurements or sensor readings. So we're going to go through some of that, some of the applications for it now. So here we have one of the simplest Wheatstone sensors available. And this one's going to be a really nice model to show some mathematical proofs behind it, and also to give you a general idea of the concept of how this is working. So in this Wheatstone sensor, we have all of the resistors equal R, so they all have the same value, except for the flexible resistor, which is going to be R plus the change in R. And the change in R can be either up or down. We're not going to specify that here. So from a conceptual level, when this system is balanced, when this entire system is balanced, there is no current flowing between V1 and V2. So what we're going to determine now is what is V out if the system is not balanced. So presuming, let's just step back again, let's presume all four of these resistors were the exact same value. If they were the exact same value, then there would be no potential difference between V out, and V out would equal 0 because there's no voltage difference between the two, no current flowing. If that's the case too, the V0 from the battery on the left-hand side going into V0 at the top is going to be split perfectly even between the left side of two resistors and the right side of two resistors, because again, they're all equal. Current wants to flow in the direction of the less resistance, but if the resistance are the exact same, it's going to flow equally through all of them. So essentially, you're going to have the same amount of current flowing through all the resistors and the same voltage drop through all the resistors. So that's for a perfectly evenly balanced case. That's when all the four R's are equal. Now we're going to look at this and say, what if the bottom right one is not equal? What if that's just a tiny bit up or a tiny bit down? And what's going to happen there is you are going to get a difference of voltage between V1 and V2. Because remember, the current wants to travel in the path of least resistance. And so if there is a greater resistance with those the two resistors on the right side, the sum of them, more current is going to flow through the left side. And so if we increase or decrease that flexible resistor, that R plus delta R, and that goes up or down, essentially you're going to change the balance in the system, and you're going to have a voltage either higher on V1 or higher on V2. And that's going to be able to determine, by solving that, what that R plus change in R is, or what the change in R is. So what we're going to do for this one, to determine V out, we are going to solve V1 equals V0 R over R plus R. And again, this is just the same circuit techniques that we've been using, V equals IR equals V equals IR. And that, if we simplify the R's out, we're going to get V0 over 2. And then we're also going to have to solve for V2. And V2 is going to equal the equation there, which is going to simplify out. Essentially, what this is saying is that it's going to keep the change in R, or the change in resistance, in this equation on the right-hand side. If you look at V1 again, the left-hand side isn't going to keep change in R because there is no change in R. It's just a resistor in series with another equal resistor. On the right-hand side, you're going to have a resistor in series with a resistor that has a change. And so V out, remember Kirchhoff's voltage law, the sum of the voltages in a loop equals 0. So we're going to have V out equals V2 minus V1. And then if you solve down through that, you're going to get V out equals about the change in voltage over 4 multiplied by the change in resistance over the resistor. And I just want to bring this up to be able to show you a quick one. We're going to do more of this in lab, actually, with the Wheatstone sensors, because I think they're really useful anytime you're trying to take measurements. But the point I want you to get from this one is that if you have a perfectly balanced system, the current is going to be the same going through the left-hand side, both R's, and the right-hand side, both R's. If you have a change in one of the resistor values, then you're going to have more current go through the lower side, the side that has the least resistance. And that's going to create a potential difference between V1 and V2. That potential difference, or V out, that we solve for here is going to show you exactly what the resistance or the change in resistance is if you know that. So it allows you to solve the system of equations. So we're going to go through another one of these later on in lab so that you get a more thorough understanding, but this is a really good slide to be able to show if you have essentially three equal resistances, how to calculate either the V out or to calculate the change in R if you know the V out. That change in resistance R plus the change in R. So this is going to come into a practical example here where we're looking at piezoresistive sensors. And so essentially what these sensors are, you can think of this from a conceptual idea too. If you remember back through the resistor equations that we have, where resistor equals the resistivity times the length over the area, if you take a tube, which is going to be shown here right at the middle at the normal resistance where there is no change in resistance and there's no force applied, if you take that tube and you stretch it, you're applying force to it, you're going to make it go longer and you're going to make the area decrease. And so that's going to change the resistivity of that cylinder. And that's what's happening when you stretch over there. And if you look at the left-hand side, if you press in on that cylinder, you're going to compress it. And as you compress it, your length is going to decrease and your area is going to decrease. And this is going to, in this case, decrease the resistance. So you see that blue line there showing the resistance versus force. You've got less resistance on the left-hand side and you've got more resistance on the right-hand side. And it's a linear relationship in this case. So if we look down at that equation, R, or the resistance, equals the normal initial resistance R0 plus the change in R. The change in R can either be from compression or stretching. It can either be decreasing the resistance from average or increasing the resistance from average. You're going to get this equation where R equals R0 times the sum of 1 plus alpha P. And so a great way of thinking about this is a stretch sensor. So we can make knitted stretch sensors in lab, and a knit stretch sensor is essentially just a conductive material that we've knit in such a way that as we stretch it, we're increasing the length, we're increasing the L, we're decreasing the area, and that resistance is going to increase. As opposed to if we let it relax again, relaxing brings it back to our average or the normal average. And we're using essentially the spring property of a knit, which is like a normal spring. As you pull it apart, it bounces back, and that bounces back has a normal average resistance. And so in lab, we're going to be able to use these string resistors or these stretch resistors and stretch fabrics to be able to determine what their specific resistance is in a circuit by using a Wheatstone bridge. So let's look a little bit more into resistors as sensors. So here we have a really cool piezo-resistive sensor and a brief breakdown of the diagram of how they work, and an actual picture of one then too, from it looks like a scanning electron microscope. So what we've done on the top side, so what we have with this is a piezoresistor is a resistor, again, that when you stretch it changes its resistance. As you deform it, it changes resistance. And so what you need is first off, a piece that is not going to change shape at all to be able to hold this resistor steady. Because if the bottom is changing and the top is changing, you're not going to know how much which one is changing, and you can't solve that. So the way we do that is take something very, very stiff, and glass substrates are very, very stiff. This could be like, essentially a lot of circuit boards are glass composites. G10, G20, G30 are different names of composites that are used in circuit boards. So we take a glass substrate underneath, and then we add some space to allow the deformation. And then in the picture you have this diaphragm, which is blue, and light blue means it's unbent, and the deeper blue means it's bent. And then you have your piezo resistor, which as it changes, as it stretches, then you're going to be able to have a change in resistance, which we measure. And so by the difference in pressure between the normal, which is that piezo resistor in light yellow on the bottom left picture, to the piezo resistor when it's pressed, which is the darker yellow underneath that, there's going to be a change in length there. There's going to be a change in motion. And that's going to stretch the resistor out, and that's going to change the resistance. And so if we look on the right, you actually have a picture from an SEM, scanning electron microscope, showing a microfabricated piezo sensor. And so these sensors are extremely small and extremely low cost, all things considered, and they give a pretty high resolution of location by stringing a bunch of them together. So there's a couple different methods. This used to be in not the new cell phones. The new cell phones are generally capacitive touch, but the old touch screens where you actually had to push on the screen and make it like a physical push, they had a lot of these piezo sensors. There's also piezo sensors in biomedical engineering whenever you're trying to do like orthotics or any studies about the foot or how the foot is landing. Because if you put piezos down and you have somebody step on them, you can get a very accurate description of where the distribution of their weight is on the pad. And there's some other cool things you can do with these as well. However, since the change in length and the change in resistance is very, very tiny, you need a good system of being able to measure what that resistance is before and after. And you also need an amplifier generally with these two, which is something we're going to get into later with op amps. But know in general for now, the Wheatstone bridge allows you to take and measure what the change in resistance is to one of these. And that change in resistance matches up to a table, and that table can tell you how much pressure you're pushing on it. Here we have another cool resistor as a sensor, and this is a resistor as a fluid flow sensor to be able to determine how much flow is happening. And these have very, very high resolutions, and you can get very, very accurate amounts of fluid flow using this technique. So on the left, we have this simple little math equation, which says the change in resistance equals K, the change in temperature. And so what this sensor, how the sensor works is, and if we remember, anytime we put current through a resistor, it gets warm. And so at its very, very base level, this, as we're putting current through this resistor, it's getting warmer, but as fluid is flowing over the resistor, that's removing heat, and we can measure then the essentially what that resistance is based on the fluid flow. So let's give an extreme case. Let's say we're using this up in space. And in space, there's no fluid flow. There's no air, there's no water. It's just hanging out there in a vacuum. If this is hanging in a vacuum and we're putting current through, the edge of this, that thin piece right above the blue arrow that says fluid flow, is getting warmer. How is that heat being removed? That heat is not being removed through convection. There is nothing to convect heat. It is being moved through conduction at the 2 points, those 2 squares that attach to the circuit board, and there's a little bit being removed in radiation as well. However, there's no convection, so that means there's no fluid flow, which makes sense because there's nothing to remove that extra amount of heat from that circuit. So that says essentially that there's zero fluid flow, which is correct. There's no air moving in space. There's no water moving in space. It's just chilling there in a vacuum. However, let's say we have a fluid flow going across that. What's going to happen? Let's just say that fluid is water. That water is going to pull away some of the heat from that very, very thin resistor there. And as we saw previously, resistance changes in regards to temperature. And so what's going to happen with this is as heat is pulled away, the more heat that is pulled away, or the faster the fluid is moving to pull heat away, what we're going to get is a very different change in resistance. Essentially, you're going to be able to suck more of that heat out of the system, and that's going to be able to be measured. And so we can use this fluid flow as a measure of how fast things are going based upon how much heat they suck from the system. And again, all of this is very, very small. You're going to have very, very small numbers, which means you have to have a very accurate way of measuring them. And the Wheatstone bridge allows you that accuracy to be able to measure. And again, usually you're going to use that Wheatstone bridge in conjunction with an amplifier system and some other digital electronics to be able to record this on a computer. But this is essentially the very, very basic concept and theory behind how these fluid flow sensors work. So here we have example 216, which is a piezo resistor cantilever system. And so this is going to show you a practical application of how to use a piezo resistor and use a Wheatstone bridge to be able to determine that value. So what we've got here in the top left is our normal Wheatstone bridge circuit, and all of our R's are the same except for the bottom right one. It's going to be able to change. That's what the delta R is signifying. And so if we get our equation for that delta R equals R0 alpha P, which means the normal resistance, or the resistance at rest, times alpha, which is the piezo resistive coefficient, which is in meters squared per newtons, and then P, which is a mechanical pressure. And if we go back to our mechanics, our basis of mechanics, mechanical pressure P equals a force times a length over a width times a height squared. And so that's just a useful thing to know, and that's how we're going to be able to solve this problem. So if we are going to solve for V out using our normal equations, our V out is going to be equal to V0 over 4 times alpha P. And do you see how we kind of got that mathematically? If not, come by in office hours and ask, or shoot me an email. But this should be a pretty easy coefficient, or a pretty easy proof there. So that V out is going to say that the change in the voltage between V1 and V2, or between these two halves of the circuit, is going to be a product of the pressure and the coefficient, which the coefficient comes from the material, or what we're using. So now that we kind of have the background for that, let's go into actually how to solve this. So the problem here says determine the output voltage of a Wheatstone bridge circuit if the force equals 50 newtons, V0 equals 1 volt, and the piezo resistor is made of silicon, and the cantilever dimensions are W equals 0.5 cm, height equals 0.5 cm, and the length equals 1 cm. So this one is pretty much a plug and chug, which is why I didn't write it out in a more involved tutorial. But what we're going to do is we're going to plug those values in that we have in order to get our V out that we have. And the V out is going to be minus 0.1 V. And so this is 400 times greater than if there's no cantilever. So essentially what this is saying is the cantilever allows more change in resistance, and it's going to allow a greater potential difference between V1 and V2. And that is going to mean that we have a better signal coming in, and we have more data coming in, as opposed to if we didn't have a cantilever. So mathematically, a lot of this comes from the fact that we're going to have that height squared on the bottom, we're going to have a width, we're going to have that length, and we're going to have the force. So that pressure is going to create more change in voltage, more of a potential difference, more change in resistance for that sensor due to its cantilever, as opposed to having just a flat piece with no cantilever action that we're pushing on.